Most of the mass in the universe is not locked inside particles themselves. Modern physics suggests that mass may arise from something far more unusual, an invisible field that fills every point of space. In July 4th, 2012, inside CERN's Large Hadron Collider, a circular machine 17 miles across, about 27 kilometers, scientists working with the ATLAS and CMS detectors reported a signal near 125 giga-electron volts. That signal revealed the first measurable trace of the Higgs boson and confirmed a deeper idea. Space itself carries structure that can slow certain particles and leave others untouched. Tonight, we explore how that structure shapes matter across the universe, beginning with, was the 4th of July 2012 discovery really a particle, or the first visible scar of an invisible field? Before we begin, if you're kind enough, a gentle like or a quiet tap on subscribe would truly mean a great deal to me. It may seem like a small gesture, but I hold it with sincere gratitude, because every bit of your support keeps this tiny universe alive and reminds me that these quiet stories still find their way to kind hearts like yours. For nearly half a century, physicists worked with a mathematical framework that described how the fundamental particles of nature interact. Yet one crucial element remained unconfirmed, and that absence pressed against the entire structure of modern particle physics like a loose stone in an otherwise stable arch. The Standard Model predicted that an invisible field should exist everywhere in space, shaping how certain particles acquire mass. But prediction alone could not close the case. Only experimental evidence could. On July 4th, 2012, inside a circular accelerator buried beneath the border of France and Switzerland, that evidence finally arrived. What the ATLAS and CMS collaborations at CERN reported that morning was formally described as the observation of a new boson with a mass near 125 giga-electron volts, divided by the speed of light squared. Yet the deeper meaning of the announcement ran far beyond the appearance of a new particle in a detector readout. The discovery indicated that empty space itself might possess a measurable structure, a field permeating the universe, whose subtle influence determines whether certain particles move as if weightless or carry inertia. The instrument that produced this moment had been under development for decades. The Large Hadron Collider, often shortened to LHC, forms a ring, approximately 27 kilometers in circumference, about 17 miles, containing superconducting magnets, cooled with liquid helium to temperatures near 1.9 Kelvin. Inside that ring, protons travel in opposite directions, guided by magnetic fields and accelerated to energies reaching several tera-electron volts. At nearly the speed of light, those protons collide within massive detectors designed to track the aftermath of the collision with extraordinary precision. ATLAS and CMS are among the largest scientific instruments ever constructed, each containing layers of silicon trackers, calorimeters, and muon chambers capable of recording the trajectories and energies of thousands of particles produced in a single collision. The logic of the search was deceptively simple. If the Higgs field truly filled space, then disturbances in that field should appear in high-energy collisions as a particle, the Higgs boson. But the path to that conclusion required immense patience. Each second inside the collider produced hundreds of millions of proton collisions, yet only a tiny fraction might contain hints of the phenomenon physicists were seeking. Over the course of years, the detectors recorded datasets containing trillions of events. Advanced algorithms filtered through this ocean of collisions, isolating patterns in which the decay products matched the expected fingerprints of a Higgs boson. By the summer of 2012, both ATLAS and CMS had independently observed an unusual excess of events clustered near the same energy value. In particle physics, statistical certainty is measured using a scale known as sigma. A 3 sigma signal might suggest an intriguing hint. A 5 sigma signal corresponds to a probability of less than 1 in 3 million that the observed effect is a random fluctuation. When the CMS collaboration reported a signal exceeding 5 sigma, near 125 giga-electron volts, and ATLAS observed a compatible result, the long search reached a turning point. The experiments had not merely glimpsed a new particle, they had cornered a prediction that had been standing inside the equations of quantum field theory since the 1960s. To understand why this mattered so deeply, it helps to look back to the intellectual environment of that earlier decade. In 1964, several physicists, including Peter Higgs, François Englert, Robert Brout, and others, proposed a mechanism explaining how certain particles could acquire mass without destroying the mathematical consistency of the electroweak theory. The equations describing electromagnetic and weak nuclear interactions possessed a symmetry that initially forced the particles in the theory to appear massless, yet the world clearly did not behave that way. The W and Z bosons that mediate the weak force carry substantial mass, and elementary particles, such as electrons, do not travel at the speed of light. Something in the structure of nature had to allow mass to emerge, while preserving the symmetry of the equations at a deeper level. The proposed answer was that space itself might contain a scalar field with a non-zero background value. Particles interacting with this field would behave as though they carried mass. The Higgs boson would represent the smallest excitation of that field. Much like a ripple on the surface of a pond reveals the presence of water beneath it. But in the 1960s, this concept remained purely theoretical. No accelerator of that era possessed the energy required to test it directly. Over the following decades, the idea became embedded in the standard model, yet experimental confirmation remained elusive. Several earlier facilities attempted to narrow the possibilities. The Large Hadron Collider at CERN, operating during the 1990s, searched for hints of the Higgs boson, but could only set lower limits on its possible mass. Later, the Tevatron Collider at Fermilab in the United States pushed the search further, excluding large regions of parameter space and suggesting that if the Higgs boson existed, it might lie near the energy scale eventually observed at the LHC. These incremental steps illustrate an essential aspect of scientific progress. Each experiment does not merely aim for discovery, it also trims away incorrect possibilities, gradually tightening the boundaries around the truth. The scale of the challenge becomes clearer when one considers the processes through which the Higgs boson can appear. In high-energy proton collisions, the Higgs particle is typically produced through interactions involving heavy quarks or through vector boson fusion. Once created, it decays almost immediately, transforming into other particles such as pairs of photons, Z-bosons, or bottom quarks. Physicists must reconstruct the presence of the Higgs indirectly by examining the energies and directions of these decay products. Each decay channel carries its own statistical challenges, background processes, and detector sensitivities. The apparent signal emerges only after immense quantities of data have been analyzed. When the CERN seminar began on July 4, 2012, the auditorium filled with researchers who had spent years contributing to the experiment. Screens displayed plots showing peaks rising above background distributions. The shape of those peaks, small but unmistakable, matched the predictions for a particle near 125 giga-electron volts. After decades of theory and decades more of experimental preparation, the data had reached the threshold required for formal discovery. Peter Higgs himself attended the announcement. As the results appeared on the screen, observers noticed that he wiped away tears. The moment captured a rare alignment between mathematical prediction and physical observation. The field concept that had once seemed speculative now possessed direct experimental support. Physicist Fabiola Gianotti, spokesperson for the Atlas collaboration at the time, summarized the significance during the presentation. We have observed a new particle consistent with a Higgs boson. Yet the discovery also raised deeper lines of investigation. The particle detected in 2012 exhibited properties consistent with the Standard Model Higgs, but the measurements had only begun. Researchers needed to determine whether the new boson decayed into the predicted combinations of particles, whether its interactions matched theoretical expectations, and whether subtle deviations might hint at physics beyond the Standard Model. Since that initial announcement, subsequent runs of the LHC have refined these measurements with increasing precision by analyzing millions of Higgs events. Atlas and CMS have confirmed multiple decay channels and measured the particle's mass with uncertainties below 0.1%. Meanwhile, astrophysical observatories such as NASA's telescopes and ESA missions contribute complementary knowledge about the broader structure of the universe. They measure phenomena ranging from cosmic microwave background radiation to the large-scale distribution of galaxies. Although these observations operate at vastly different energy scales than particle accelerators, together they help test whether the Standard Model and its extensions remain consistent with the universe we observe. The Higgs field may influence processes that occurred fractions of a second after the Big Bang, shaping how matter evolved as the universe cooled. Consider a practical illustration. If the Higgs field did not exist, the W and Z bosons would remain massless. Without their mass, the weak nuclear force would behave very differently, extending over long distances rather than acting only at subatomic scales. Such a change would alter nuclear reactions inside stars and likely prevent the formation of stable atoms as we know them. The presence of the Higgs field, therefore, connects microscopic particle interactions to the large-scale conditions that allow galaxies, stars, and planets to form. Another intriguing detail lies in the energy scale itself. A mass of 125 giga-electron volts corresponds to roughly 130 times the mass of the proton. That value places the Higgs boson in an unusual position among known particles. It is far heavier than most elementary fermions, but much lighter than the energy scale, where new symmetries might emerge in grand unified theories. Physicists continue examining whether this mass hints at deeper principles, or whether it represents a parameter that must simply be measured. The story does not end with confirmation of the Higgs particle. The field it represents may interact with other phenomena not yet fully understood. For instance, the Higgs field could play a role in the stability of the universe's vacuum state. Calculations suggest that the measured Higgs mass lies near a boundary separating stable and metastable configurations of the vacuum. This observation has prompted careful analysis of how quantum fluctuations and interactions with other fields might influence the long-term evolution of space-time. All these lines of investigation trace back to that moment when a narrow peak appeared in the data from proton collisions beneath the Franco-Swiss border. What seemed at first like the detection of a single particle gradually unfolded into evidence for a pervasive structure woven through space itself. The discovery reshaped how physicists discuss mass, inertia, and the behavior of matter at its most fundamental level. The Higgs boson is now listed among the known particles of the Standard Model. Yet one tension continues to attract attention. If this particle represents only the smallest observable disturbance of a deeper field, then the discovery at CERN may not have marked the end of the search. Instead, it may have revealed the first measurable ripple of a deeper structure in which the universe is built from fields rather than solid objects, an idea explored further in If a Particle is Only a Ripple. Then what was actually found at CERN? What if the deepest mistake in modern science education was never about a wrong number, but about a wrong picture? Because the universe may not be built from tiny solid bits at all, and the object announced at the Large Hadron Collider in 2012 may have been important precisely because it forced that picture to break. Most people first meet particle physics through a simple image. Electrons are shown as little spheres. Quarks are shown as smaller spheres. Photons are shown as packets shooting across space. It is a useful first step, but only a first step. The harder and more exact story, the one modern physics actually uses, is that nature is described not by isolated pellets moving through emptiness, but by fields spread throughout space. A particle is what we call the smallest allowed disturbance in one of those fields. That change in language sounds small. It is not small. It changes what matter is, what emptiness is, and what the Higgs boson meant when it appeared in the data. To see why, it helps to begin with an ordinary example from daily life. When you stand near a still lake, the water looks flat and continuous. If a drop falls into it, circular ripples move across the surface. No one thinks the ripple is a separate substance added on top of the water. The ripple is simply a moving pattern in something that was already there. In modern quantum field theory, the electron field, the photon field, the quark fields, and the Higgs field play a role somewhat like that lake. The particle is not the underlying stuff. The field is the underlying stuff. The particle is the measurable ripple. That is why the Higgs boson matters so much. It was not merely one more entry in a particle table. It was the first direct, detectable ripple of the Higgs field. This way of thinking did not appear overnight. The path began in the early 20th century, when physicists found that older pictures of nature were no longer sufficient. In the 19th century, James Clerk Maxwell had shown that light behaves as a wave in an electromagnetic field. Then, in 1900, Max Planck discovered that light energy is emitted in discrete amounts. In 1905, Albert Einstein used that idea to explain the photoelectric effect, treating light in some situations as if it came in individual quanta. Then came Louis de Broglie in 1924, proposing that matter itself has wave-like properties. Soon after, experiments confirmed that electrons produce interference patterns, just as waves do. The old division between particles and waves had begun to fail. A decisive moment came in 1927, when Clinton Davison and Lester Germer observed electron diffraction, showing that electrons can behave like waves when scattered from a crystal. This was not a philosophical preference. It was a measured pattern on an instrument. Electrons, which had often been pictured as localized bits of charge, could spread, interfere, and then arrive at the detector in discrete events. The universe was already telling physicists something difficult but exact. The basic ingredients of nature do not obey the common sense categories built for stones, dust, or raindrops. They follow quantum rules. Yet even wave mechanics was not the final layer. A further step became necessary once quantum theory was combined with special relativity. If a theory is to describe particles moving close to the speed of light, creating and destroying each other in high-energy collisions, then fixed particle numbers are no longer enough. A more general framework is required. That framework is quantum field theory. In it, every type of fundamental particle corresponds to a field filling all of space. The electron is an excitation of the electron field. The photon is an excitation of the electromagnetic field. Quarks are excitations of quark fields. And the Higgs boson is an excitation of the Higgs field. This is not just a tidy mathematical rewording. It explains phenomena that the older picture struggles to hold together. Consider the vacuum. In everyday speech, vacuum means nothingness. In modern physics, the vacuum is the lowest energy state of the fields. It is not a region where reality switches off. It is a region where no detectable excitations are present. That sounds technical, but the experimental meaning is plain. Even in the quietest possible state, the fields remain there. Their allowed structures remain there. Their interactions remain there. The stage is never absent. Only the visible ripples may be absent. This is one reason the Higgs discovery reached so deeply into the foundations. It implied that what we call empty space is not empty in the ordinary sense. It has content. It has order. It has a background structure that can be tested. Richard Feynman, who helped build the modern language of quantum electrodynamics, once said, "I think I can safely say that nobody understands quantum mechanics." That line is often repeated for drama, but the better use of it is caution. It reminds us that the mathematics is reliable long before the imagery becomes comfortable. Quantum field theory does not ask for comfort. It asks for precision. And its precision is extraordinary. Predictions for the magnetic properties of the electron agree with experiment to astonishing accuracy. The quantum field picture is not accepted because it sounds elegant. It is accepted because it works with brutal consistency. Now bring that framework back to the Large Hadron Collider. When protons collide at very high energies, the collision does not resemble two tiny billiard balls touching and breaking apart. A proton is itself a restless system of quarks and gluons. At high energy, what collides are field excitations interacting through the rules of quantum fields. The aftermath is a spray of new excitations, some common, some rare. Detectors such as the toroidal Large Hadron Collider apparatus and compact muon solenoid do not photograph particles in the everyday sense. They record tracks, energy deposits, decay products, and timing information. From these patterns, physicists reconstruct what kinds of field excitations were produced for a fleeting instant. So when the Higgs boson was reported, what had really been found was evidence that the Higgs field had been excited strongly enough, briefly enough, and cleanly enough for its ripple to be inferred from the debris. This distinction matters because it prevents a familiar misunderstanding. Many people hear Higgs boson and assume that the boson itself is what gives mass to the universe, as though a rare particle hidden in a machine were somehow responsible for the weight of ordinary matter. That is not the main mechanism. The field is what matters first. The boson is the visible disturbance that reveals the field. This is close to the difference between proving the existence of air by detecting a sound wave and then mistaking the wave for the medium itself. The sound is evidence. The air is the underlying presence. In the same way, the Higgs boson is evidence that the Higgs field is real. It is also worth asking why matter looks solid if the underlying description is field-like. The answer comes from quantization and interaction. Fields do not vibrate in arbitrary ways. They are restricted to specific allowed excitations. Those excitations carry definite energies, momenta, charges, and spins. When many such excitations interact through electromagnetic forces, quantum statistics, and nuclear forces, they build atoms, molecules, crystals, liquids, and living tissue. Solidity is not an illusion in the sense of being false. It is an emergent behavior, but it is not fundamental in the way everyday language suggests. Matter feels continuous and rigid because fields, under quantum rules, can organize themselves into extremely stable structures. Take the chair beneath a person sitting at rest. It feels firm, stable, resistant. Yet the chair is mostly empty space at the atomic scale, with electrons occupying quantum states around nuclei. The resistance you feel is not tiny hard balls grinding against each other like sand. It comes largely from electromagnetic interactions and from the exclusion principle that prevents electrons from being packed into the same quantum state. The chair's firmness is real. The microscopic picture is simply far less intuitive than ordinary touch suggests. This is the larger intellectual turn opened by the Higgs story. Once fields become central, the old image of matter as compact little pellets becomes too shallow to carry the full weight of the evidence. The history of the Higgs field itself sharpens this point. In the 1960s, several theorists were trying to understand how the weak force could be described by a mathematically consistent gauge theory, while still allowing the carriers of that force to be massive. A massless carrier would lead to very different behavior. The eventual solution involved a field spread across all space with a non-zero background value. Particles interacting with that background would behave as if they possess mass. The Higgs boson would appear as a small oscillation around that background. This was a daring move because it placed a new field not inside matter, not only in stars or colliders, but everywhere. The field was not added to describe one rare event. It was added to explain the quiet, constant structure of the vacuum itself. For decades, that idea remained incomplete without direct evidence. The standard model worked extremely well, but the Higgs field still lacked its visible ripple. Then the Large Hadron Collider reached the necessary energies. On the 4th of July in 2012, the new boson appeared near 125 giga-electron-volts. Later measurements strengthened the case that its properties matched those expected for the Higgs boson. Its decay into pairs of photons, its decay into Z bosons, and its spin and parity all pointed in the same direction. The field picture had survived one of the hardest experimental tests ever designed in particle physics. There is another reason this shift from particles to fields deserves careful attention. It changes how one thinks about identity in nature. A photon created in a distant star and a photon created in a laboratory are not different species of tiny objects stamped in different places. They are excitations of the same electromagnetic field. Likewise, every electron in the universe is an excitation of one electron field. This helps explain why electrons are identical everywhere we test them, whether in terrestrial laboratories, in solar plasmas observed by the National Aeronautics and Space Administration, or in extreme astrophysical environments studied through space telescopes and ground observatories. The sameness is not accidental. It is built into the field description from the start. The deeper one follows this trail, the harder it becomes to keep the old image of nature. We speak of particles because detectors click in localized places, because tracks curve in magnetic fields, because decay products can be counted. Those are real observations. But beneath them is a framework in which fields are primary, and particles are the smallest measurable packets of their behavior. That is why the discovery at the Large Hadron Collider was not just the addition of one more particle to a list. It was a measured sign that the vacuum has architecture, that matter's apparent solidity comes from permitted modes of vibration. and that the Higgs boson was never the full story, only the first visible tremor of something that had already been filling the universe all along. And once that much is granted, another pressure point comes into view with unusual force. Because if a particle is only a ripple in a field, then the next step cannot stop at naming the ripple, but must press into the harder territory, opened by why do some ripples travel like light, while others carry mass from the start? Why does one ripple of nature race through the universe at the speed of light, while another begins its journey, already carrying weight, already resisting motion, already behaving as though space itself is holding it back? The answer lies not in a hidden ingredient sprinkled into the equations of physics, but in the deeper structure that determines how a field is allowed to oscillate. When modern physics describes particles as excitations of fields, it does not stop at saying that ripples exist. It also asks how those ripples move, what frequencies they can have, and whether the field itself permits vibrations that begin at zero energy or requires a minimum energy before any motion can occur. That simple difference separates the massless from the massive and reveals that mass is not an afterthought added to matter. It appears as a structural property of the field itself. To see this clearly, it helps to begin with something familiar. Imagine a long stretched string fixed at both ends. If the string is plucked gently, waves travel along it. The wave can have many frequencies, depending on how the string vibrates. Yet there is a lowest tone that the string naturally supports. Below that tone, the string simply cannot vibrate in a stable pattern. The physics of the string itself sets that limit. Fields in nature behave in an analogous way, though in a far more subtle and mathematical sense. Some fields permit oscillations starting from zero frequency, meaning a disturbance can exist with arbitrarily small energy. Other fields require a baseline frequency before oscillations can occur at all. That baseline, once the field is described using quantum theory, becomes what physicists call rest mass. This distinction was not obvious when scientists first explored the wave nature of matter. In the early 20th century, researchers such as Louis de Broglie realized that particles possess wave-like behavior. Experiments soon confirmed that electrons form interference patterns when passed through narrow slits, much like light does. Yet something curious appeared when physicists examined how these waves propagate. Light waves move at a constant speed in empty space, roughly 300,000 kilometers per second. Electrons do not. They can move slower, accelerate, or remain bound inside atoms. The difference between those behaviors hinted that not all waves in nature obey the same rule. As quantum field theory matured during the 1930s and 1940s, physicists learned that each field possesses its own wave equation. In simple language, that equation describes how disturbances in the field evolve in time and space. When the equation allows oscillations of arbitrarily small frequency, the corresponding particle behaves as massless. Photons are the most familiar example. They travel at the speed of light in vacuum because the electromagnetic field does not impose a minimum frequency requirement on its oscillations. A photon can carry extremely small energy, limited only by measurement precision. Contrast this with fields whose wave equations require a baseline frequency. In those cases, the field cannot vibrate unless the oscillation reaches a certain threshold energy. That threshold becomes the particle's rest mass. Even if the particle is not moving through space, the field must still oscillate with that minimum frequency. It is as though the field insists on maintaining a background rhythm. When the ripple moves through space on top of that rhythm, the particle behaves as a massive excitation. This insight transforms the meaning of mass. Instead of thinking of mass as a material ingredient stored inside an object, quantum field theory describes it as a consequence of how a field vibrates. The allowed oscillations of the field determine whether the ripple travels like light or behaves as matter with inertia. The concept sounds abstract, but it can be connected to experiments performed across many decades. Consider the photon once more. Observations from astronomical instruments operated by the National Aeronautics and Space Administration and the European Space Agency repeatedly confirm that light travels through interstellar space at a constant speed, independent of energy. Measurements of gamma rays from distant supernova explosions and from energetic galaxies billions of light-years away show that high-energy photons and lower-energy photons arrive essentially simultaneously, despite traveling immense distances. These observations place extremely tight limits on any possible photon mass. If the photon possessed even a tiny rest mass, waves of different energy would propagate differently over cosmic scales. Yet observations show that they do not. The electromagnetic field therefore behaves as a field whose oscillations begin at zero frequency. Now examine a massive particle such as the electron. Electrons can be accelerated in laboratory experiments and inside astrophysical environments. When researchers measure the relationship between the electron's energy and its motion, they find that even an electron at rest carries an intrinsic energy associated with its mass. This intrinsic energy does not vanish when the particle stops moving. It arises from the baseline oscillation of the electron field itself. In the language of field theory, the electron field cannot vibrate below a specific frequency determined by its mass. The ripple cannot disappear into nothingness. The field insists on maintaining that minimum rhythm. The distinction becomes even clearer in particle accelerators. Inside facilities such as the Large Hadron Collider, protons are accelerated until their energy reaches trillions of electron volts. When these protons collide, the energy released can excite many different fields simultaneously. Photons appear as massless excitations traveling outward at the speed of light. Heavy particles such as W bosons, Z bosons, or top quarks appear only when the collision energy exceeds their rest mass thresholds. The detectors do not see equations or abstract fields. They see tracks, energy deposits, and decay products. Yet behind those patterns lies the same principle. Each particle's mass corresponds to the minimum oscillation frequency allowed by its field. This concept gained further credibility through decades of precision experiments. Observatories studying cosmic rays have detected particles with masses predicted by quantum field theory. Particle accelerators have measured how energy and momentum relate for both light-like and massive excitations. Each observation fits the same framework. Fields whose oscillations begin at zero frequency produce particles that travel at light speed. Fields requiring a baseline frequency produce particles with rest mass. The Higgs field introduces an additional layer to this story. Certain fields in the Standard Model begin as massless in the underlying symmetry of the theory. Their equations initially resemble those of massless waves. Yet when the Higgs field settles into a non-zero background value, interactions with that background alter the allowed oscillations of those fields. The baseline frequency appears where none existed before. The ripple acquires mass not because a number was inserted artificially into the equations, but because the structure of the interacting fields has changed. The oscillation rules themselves have shifted. Historical accounts from the 1960s reveal how surprising this idea was when first proposed. Physicists were searching for a way to preserve mathematical symmetries in the electroweak theory, while explaining why the carriers of the weak force are massive. Peter Higgs, François Engler, Robert Brout, and others realized that a field with a constant background value could modify the oscillation behavior of other fields. What had looked like massless waves would then behave as massive ones once the background field was taken into account. The mathematics suggested that a new scalar field should exist everywhere in space. The Higgs boson would be the ripple associated with that field. Decades later, the Large Hadron Collider provided the experimental evidence needed to confirm that prediction. The discovery of a boson near 125 giga-electronvolts did not simply add another particle to the catalogue of matter. It showed that the Higgs field is real and that the oscillation rules governing other fields are shaped by its presence. When physicists analyze how the W and Z bosons move, their masses match precisely the pattern predicted if those particles are ripples in fields interacting with the Higgs background. The consequences extend beyond the laboratory. Observations of the early universe indicate that particle interactions played a crucial role during the first fractions of a second after the Big Bang. Data from cosmic microwave background studies performed by missions such as the Planck satellite of the European Space Agency reveal how energy moved through primordial fields as the universe cooled. The behavior of massive and massless excitations influenced how matter formed and how forces separated into the forms we observe today. The wave properties of fields therefore connect the physics of particle accelerators with the evolution of the cosmos itself. The clarity of this framework led the astronomer Carl Sagan to emphasize a central lesson about science. He once wrote that extraordinary claims require extraordinary evidence. In the case of quantum fields, that evidence has accumulated across experiments in laboratories, observations of cosmic radiation, and measurements of particle interactions. Each result strengthens the same conclusion. Mass is not a decorative label placed on matter. It arises from the allowed oscillation patterns of the fields that fill the universe. From this viewpoint, the contrast between massless and massive particles becomes less mysterious. The photon travels freely because the electromagnetic field allows oscillations beginning at zero frequency. The electron resists motion because its field demands a baseline oscillation energy. The W and Z bosons carry even greater mass because their interactions with the Higgs field alter their oscillation patterns further. These differences emerge from the structure of the fields themselves, rather than from hidden substances embedded inside particles. As experiments continue to refine measurements of particle properties, physicists examine the wave equations and interaction patterns of fields with increasing precision. Detectors at the Large Hadron Collider now record millions of events involving Higgs bosons, allowing researchers to test whether the field behaves exactly as predicted or whether subtle deviations hint at deeper physics beyond the standard model. Each new measurement probes the structure that determines which ripples remain massless and which must carry mass from the moment they appear. Following this line of reasoning leads to a more demanding implication. If mass arises from the allowed oscillations of a field, then understanding the origin of mass requires more than studying those oscillations alone. It also requires examining the deeper structure that allows such oscillations to exist in the first place. This leads to a deeper question. Did physicists put mass into the equations by hand, or does it emerge from the shape of reality itself? Did physicists secretly place mass into their equations by hand, like an adjustable knob that could be turned until theory matched experiment? Or does mass emerge automatically from the deeper structure of the fields that fill the universe? This question appears technical at first glance, yet it strikes directly at the credibility of modern physics. If mass were merely inserted as a convenient parameter, then the standard model would be little more than a carefully tuned machine. But if mass arises from the internal geometry of the field itself, then the theory reveals something deeper about the structure of reality. The answer lies in a concept that sounds abstract at first, but becomes remarkably concrete once examined closely. That concept is the potential of a field. In classical physics, a potential describes how energy changes as a system moves through different configurations. A familiar example appears in gravity near Earth. When a stone is lifted above the ground, it stores gravitational potential energy. If the stone is released, gravity pulls it downward. The force arises because the energy changes with height. The steeper the energy landscape, the stronger the force pulling the object toward a stable position. This idea of an energy landscape appears throughout physics. Springs possess it. Electric charges experience it. Planetary motion follows it. And in modern quantum field theory, every fundamental field also possesses its own potential. A field potential describes how the energy of a field changes depending on the value the field takes at a given point in space. When the field deviates from its lowest energy configuration, the potential produces a restoring influence that pushes the field back toward equilibrium. That restoring influence determines how the field oscillates. And those oscillations, when quantized, become particles. The remarkable conclusion follows naturally. The mass of a particle is determined by how sharply the potential curves around its resting value. This statement can be understood without writing a single symbol. Imagine once again a stretched spring attached to a wall. If the spring is displaced slightly from its resting position, it pulls back with a certain stiffness. A stiff spring produces rapid oscillations. A soft spring produces slower ones. The stiffness determines the natural vibration frequency. In quantum physics, that vibration frequency translates directly into energy. The baseline energy of that vibration corresponds to the mass of the particle associated with the field. In this way, curvature in the potential becomes inertia in the particle. The connection may sound surprising, but it emerges from the mathematics of field equations in a straightforward way. When physicists analyze how a field evolves in time, the equation describing that evolution includes a term that comes from the slope of the potential. The slope tells the field how strongly it should move back toward equilibrium when displaced. Near the resting point of the potential, the slope changes at a rate determined by the curvature of the energy landscape. That curvature governs the frequency of the smallest oscillations. Once quantum mechanics enters the picture, those oscillations correspond to discrete energy packets. Those packets are particles, and their energy at rest is what we measure as mass. The importance of this relationship became clear during the development of quantum field theory in the mid-20th century. Physicists were attempting to construct theories that could describe particles and forces consistently with both quantum mechanics and special relativity. They discovered that writing down a field equation without specifying a potential left the behavior of the field incomplete. The potential defined the equilibrium value of the field and the restoring influence acting on disturbances. Without it, the theory could not predict whether the associated particle would be massless or massive. In the 1950s and 1960s, theorists studying scalar fields began to explore how different shapes of potential lead to different particle properties. A scalar field is one that has a value at every point in space, but no directional orientation. Temperature in a room is a simple everyday example of a scalar quantity. In particle physics, the Higgs field is the most famous scalar field. By examining how its potential behaves near equilibrium, physicists realized that the curvature of that potential would determine the mass of its quantum excitation. the Higgs boson. Historical records from this period reveal how these ideas slowly converged. Several researchers working independently recognized that the potential of a field could allow the vacuum itself to take on a non-zero value. Robert Brout and François Englert in Belgium, Peter Higgs in the United Kingdom, and Gerald Guralnick, Carl Hagen, and Thomas Kibble in the United States all explored versions of this mechanism in 1964. Their work showed that when a scalar field settles into a particular minimum of its potential, the oscillations around that minimum behave like particles with specific masses. The argument was subtle because it required treating empty space as an active participant in physics. In classical thinking, vacuum was simply the absence of matter. Quantum field theory revealed a different picture. Fields remain present even in the vacuum state. The potential of those fields determines where the vacuum sits within the energy landscape. If the potential has a minimum away from zero, the field naturally settles there. Small oscillations around that minimum become observable particles. The Large Hadron Collider provided a decisive test of this framework. When proton collisions reached sufficiently high energies, detectors such as a toroidal Large Hadron Collider apparatus and compact muon solenoid recorded decay patterns consistent with a scalar particle of mass near 125 giga-electron-volts. Detailed analysis of the particle's interactions showed that its properties matched those predicted for the Higgs boson. The curvature of the Higgs potential around its vacuum value therefore corresponds directly to the measured mass of this particle. The discovery was not merely a triumph of experimental technique. It confirmed that the mass of at least one fundamental particle arises from the structure of the potential governing its field. Physicists did not insert that mass by hand after the fact. They predicted that if the Higgs field existed with a particular potential shape, then a particle with a specific range of mass would appear in high-energy collisions. The collider experiments found precisely such a particle. Evidence supporting the field framework also appears far beyond particle accelerators. Observations of cosmic radiation, measured by satellites operated by the National Aeronautics and Space Administration and the European Space Agency, reveal how particle masses influence processes in the early universe. The cosmic microwave background, mapped with extraordinary precision by the Planck mission, carries subtle patterns that depend on the properties of fundamental particles present shortly after the Big Bang. The behavior of these particles is consistent with the mass values predicted by quantum field theory. The James Webb Space Telescope continues to extend these observations by examining galaxies that formed only a few 100 million years after the Big Bang. The formation of those early galaxies depends on the behavior of matter composed of particles with definite masses. The field potentials that determine those masses therefore play a role not only in microscopic experiments, but also in the large-scale evolution of the universe. This interplay between theory and observation illustrates why the concept of potential carries such explanatory power. By specifying the energy landscape of a field, physicists determine how that field oscillates, how it interacts with others, and what mass its excitations possess. The curvature near the minimum of the potential acts like a fingerprint of the particle associated with the field. Carl Sagan once emphasized the importance of this kind of reasoning when he wrote that, "Science is a way of thinking much more than it is a body of knowledge." The statement captures the method used in modern particle physics. Researchers do not simply catalog particles and their masses. They search for the structural principles that make those masses inevitable consequences of deeper rules. In this light, the Higgs field becomes more than a single component of the Standard Model. It illustrates how properties that appear intrinsic to particles, can actually arise from the geometry of the energy landscape in which the fields reside. When the field rests at the minimum of its potential, small oscillations reveal the mass of its quanta. The particle's inertia reflects the curvature of the underlying potential. The idea continues to guide current research. Physicists now examine whether the Higgs potential might contain additional structure beyond the simplest form predicted by the standard model. Subtle deviations in Higgs boson interactions could hint at new fields or new symmetries waiting to be discovered. Each measurement from the Large Hadron Collider adds another piece of evidence, refining our understanding of the energy landscape that shapes the universe. As this investigation continues, another problem becomes difficult to ignore. If the curvature of a field potential determines the mass of its particles, then the next issue concerns the position where the field settles. Why does the field choose that value in the first place? This question leads to the exploration titled, "If empty space settles somewhere, why doesn't it settle at zero?" What if the quiet vacuum surrounding every atom, every galaxy, and every beam of light is not resting at nothing, but is instead sitting on a hidden background value that quietly shapes the mass of the universe? This possibility lies at the heart of the Higgs field. The equations describing that field contain a potential landscape, and like any system influenced by such a landscape, the field naturally settles where the slope of that energy surface becomes flat. That resting point is called the vacuum state. In many simple physical systems, the lowest energy configuration sits at zero. The field becomes calm only when its value vanishes. Yet the Higgs field follows a different rule. Its lowest energy position does not lie at zero at all. Instead, the field stabilizes at a constant background value spread throughout space. To understand the meaning of this statement, it helps to recall how physical systems behave when influenced by an energy landscape. Imagine placing a marble inside a bowl. The marble rolls until it reaches the lowest point of the surface. At that location, the slope disappears. The marble remains there because any small displacement produces a restoring force that pushes it back toward equilibrium. This picture captures the central idea behind the potential of a field. The field naturally relaxes into the configuration where its energy becomes minimal. That configuration defines the vacuum state of the field. In the standard model of particle physics, the Higgs field does not minimize its energy at the center of the bowl. Instead, the potential resembles a surface where the lowest energy points form a ring around the center. When the universe cooled after the earliest moments following the Big Bang, the Higgs field moved toward one of those lowest energy positions. Once it settled there, the value of the field across empty space became fixed at approximately 246 giga-electron-volts when expressed in energy units commonly used in particle physics. That number may appear mysterious, but it carries measurable consequences that can be observed in laboratories and in astrophysical environments. The remarkable part of the story is that physicists inferred this value decades before the Higgs boson itself was detected. In the 1960s and 1970s, researchers studying the electroweak theory discovered that the masses of the W and Z bosons depended directly on the background value of the Higgs field. When experimental measurements of those boson masses became available, theorists could work backward to estimate the magnitude of the Higgs field's vacuum expectation value. The calculations consistently pointed to a value near 246 giga-electron-volts. This meant that long before the Higgs boson appeared in detector data, scientists already suspected that empty space contained a hidden background field with a specific strength. The prediction was not guesswork. It emerged from a network of measurements and theoretical relationships linking particle masses and interaction strengths. When experiments at particle accelerators measured the properties of the weak force carriers. The numbers fit precisely with the idea that a scalar field permeates space with a non-zero equilibrium value. If the vacuum expectation value had been zero, the masses of those particles would vanish, and the weak force would behave in a radically different manner. Yet the observed world clearly shows that W and Z bosons are massive. Their measured masses match the value predicted if the Higgs field sits at that non-zero background. The implications of this insight extend far beyond collider experiments. The vacuum expectation value of the Higgs field influences how fundamental particles interact in the earliest moments of the universe. Observations of the cosmic microwave background radiation, measured with extraordinary precision by the Planck satellite of the European Space Agency, provide a detailed picture of the universe when it was only a few 100,000 years old. The pattern of temperature fluctuations in that radiation reflects the behavior of particles and forces during the earlier phases of cosmic evolution. The success of the Standard Model in explaining those patterns indirectly supports the framework in which the Higgs field maintains a constant background value throughout space. The presence of this background field also affects how matter forms in the modern universe. The masses of quarks and leptons, which depend on their interaction with the Higgs field, determine the stability of atoms and the processes occurring in stars. Without the Higgs vacuum expectation value, electrons would have no mass and could not form stable atomic orbitals around nuclei. Stars would burn differently, chemical reactions would follow unfamiliar pathways, and the structures observed by telescopes such as the James Webb Space Telescope might never emerge in their present form. The quiet value of the Higgs field therefore influences everything from the behavior of subatomic particles to the formation of galaxies. The idea that empty space possesses a measurable property was once considered radical. For centuries, physicists imagined vacuum as a stage devoid of substance. The development of quantum field theory changed that perspective. Fields remain present even when no particles are detected. Their lowest energy configuration defines the vacuum. In the case of the Higgs field, that configuration involves a constant value that fills the entire observable universe. Carl Sagan once wrote that somewhere, something incredible is waiting to be known. The discovery of the Higgs boson at the Large Hadron Collider in 2012 brought scientists closer to understanding that hidden background. Detectors known as a toroidal Large Hadron Collider apparatus and compact muon solenoid observed decay patterns, revealing a scalar particle consistent with the oscillation of the Higgs field around its vacuum value. Those measurements confirmed that the field predicted decades earlier was not merely a mathematical convenience, but a real feature of nature. What makes this discovery particularly striking is the sequence of reasoning that preceded it. Physicists first examined how particles interact through the electroweak force. From those interactions, they deduced that a scalar field must exist. From the properties of known particles, they estimated the magnitude of the field's background value. Only later did experiments reveal the ripple associated with that field. The Higgs boson appeared as the oscillation around a vacuum value that scientists had already predicted with remarkable accuracy. The concept of vacuum expectation value also connects to deeper questions about the early universe. During the first fractions of a second after the Big Bang, temperatures were so high that the Higgs field likely behaved differently. Many cosmological models suggest that at extremely high temperatures, the field temporarily rested at zero. As the universe expanded and cooled, the potential landscape changed shape, allowing the field to settle into its present non-zero value. This transition would have altered the behavior of fundamental particles and may have influenced processes such as baryogenesis the phenomenon responsible for the excess of matter over antimatter observed today. Evidence for these early cosmic conditions appears in multiple observational programs, measurements of large-scale structure, galaxy distributions, and cosmic microwave background fluctuations all align with theoretical models in which the properties of fundamental fields evolved during the early universe. The vacuum expectation value of the Higgs field is therefore not only a parameter within particle physics. It forms part of the framework describing how the cosmos developed from an extremely hot initial state into the structured universe seen today. Even now, physicists continue examining whether the Higgs vacuum remains completely stable over cosmic timescales. Calculations based on the measured mass of the Higgs boson and the top quark suggest that the universe may exist in a state that is stable but delicately balanced. Tiny variations in those masses could alter the shape of the Higgs potential and change the location of its minimum. While current data indicate that the vacuum is stable for times far exceeding the age of the universe, the question illustrates how closely particle physics and cosmology remain connected. The presence of a non-zero background field in empty space therefore represents one of the most profound insights of modern science. Space is not an empty container. It contains fields whose equilibrium values shape the masses and interactions of the particles composing matter. The Higgs field provides the clearest example. Its vacuum expectation value, near 246 giga-electron-volts, sets the scale for the masses of several fundamental particles and influences the structure of the physical laws governing the universe. When researchers examine the quiet vacuum surrounding them, they are therefore not looking at nothingness. They are observing the calm surface of a field that carries a hidden background value. The Higgs boson appears only when that surface is disturbed, yet the field itself remains present everywhere, defining a constant environment in which particles acquire their properties. Once the idea of a non-zero vacuum value is considered, the next issue concerns the mechanism behind it. If a field resting in empty space can give mass to other fields through interaction, then the explanation must examine how that interaction actually works. This leads to the question explored in how can a massless field suddenly become massive without breaking the logic of the theory? How can a field that begins completely massless suddenly behave as if it carries weight, inertia, and resistance to motion without violating the mathematical logic that defines the theory itself? At first glance, this sounds impossible. If a field has no mass in its fundamental description, then adding mass later would seem like altering the rules after the game has begun. Yet modern particle physics shows that such a transformation can occur naturally when fields interact with one another. The key lies in the phenomenon known as the Higgs mechanism, where the interaction between two fields changes the allowed oscillations of one of them. In this framework, mass is not a built-in label attached to a particle from the beginning. Instead, it appears as a consequence of interaction with a background field that already fills space. To understand how this works, physicists often begin with a simplified model involving two interacting fields. One of them behaves like the Higgs field, capable of settling into a non-zero value throughout the vacuum. The other field initially behaves like a massless wave, similar to the photon before the structure of the Higgs field becomes relevant. At the level of fundamental equations, this second field begins with no intrinsic mass term. Its oscillations resemble those of a wave that can propagate freely with no minimum energy requirement. But once the two fields interact, the situation changes dramatically. When the Higgs field settles into its vacuum expectation value, it creates a constant background environment. The second field now interacts with that background everywhere in space. The mathematics describing this interaction modifies the effective oscillation pattern of the field. Even though the original equation contained no explicit mass, the interaction produces behavior equivalent to 1. The ripple that once moved like a massless disturbance now behaves as if it possesses inertia. The idea can be understood by returning to a familiar physical analogy. Imagine a swimmer moving through still water. When the water is calm and frictionless, the swimmer could in principle glide without resistance. But if the water becomes thick or filled with currents, the swimmer experiences drag. The swimmer's own properties have not changed. What changed is the environment through which the motion occurs. In a similar way, a particle interacting with the Higgs field moves through a background that alters how its field oscillates. The effect appears mathematically as mass. This insight emerged during the development of the electroweak theory in the 1960s. Physicists were attempting to describe two fundamental forces, electromagnetism and the weak nuclear interaction, within a unified framework. The symmetry of the equations required that the carriers of the force initially behave like massless fields. Yet experiments clearly showed that the W and Z bosons responsible for weak interactions are extremely massive particles. Their masses are nearly 100 giga-electron volts, thousands of times heavier than an electron. Reconciling this observation with the mathematical symmetry of the theory became one of the central challenges of particle physics. The breakthrough came when theorists realized that a scalar field with a non-zero vacuum value could alter the behavior of other fields through interaction. Robert Brout and François Englert in Belgium, Peter Higgs in the United Kingdom, and Gerald Guralnick, Carl Hagen, and Thomas Kibble in the United States independently explored versions of this mechanism in 1964. Their work showed that when a background field exists everywhere in space, the equations governing other fields can effectively acquire terms that behave like mass. Importantly, the underlying symmetry of the theory remains intact. The apparent mass emerges from the interaction rather than from a fundamental violation of the equations. The Large Hadron Collider later provided direct experimental support for this idea. When protons collide at extremely high energies, they create conditions capable of exciting the Higgs field. Detectors such as a toroidal Large Hadron Collider apparatus and compact muon solenoid recorded events consistent with the production of a scalar particle near 125 giga-electron volts. The properties of this particle match those predicted for the Higgs boson, the quantum ripple associated with the Higgs field. Its discovery confirmed that the background field responsible for the Higgs mechanism exists throughout the universe. The implications of this mechanism are profound. The masses of the W and Z bosons arise from their interaction with the Higgs field. Fermions, such as electrons and quarks, also acquire mass through similar interactions, known as Yukawa couplings. Each particle interacts with the Higgs field with a specific strength. The stronger the interaction, the greater the effective mass that emerges. This explains why the top quark, which couples very strongly to the Higgs field, has a mass of roughly 173 giga-electron volts, while the electron, whose coupling is far weaker, has a mass of only about half a mega-electron volt. Observations across many areas of physics support this framework. Measurements of particle interactions in accelerators confirm the predicted strengths of these couplings. Precision experiments studying weak nuclear processes match the mass values expected from electroweak symmetry breaking. Astrophysical observations also depend indirectly on the masses of these particles. For example, nuclear reactions powering stars rely on the properties of quarks and electrons, whose masses arise through their interaction with the Higgs field. Observatories operated by the National Aeronautics and Space Administration and the European Space Agency study stellar processes whose behavior would be dramatically different if these masses did not exist. Cosmological evidence also connects to this mechanism. Data from the cosmic microwave background radiation, measured with extraordinary precision by missions such as the Planck satellite, reveal conditions in the early universe that depended on the masses of fundamental particles. During the first fractions of a second after the Big Bang, temperatures were so high that the Higgs field likely behaved differently from its current state. As the universe cooled, the field settled into its non-zero vacuum value. This transition altered the masses of particles and influenced how matter evolved. The large-scale structure of galaxies observed today carries subtle traces of these early physical processes. Carl Sagan once remarked that somewhere, something incredible is waiting to be known. The Higgs mechanism represents one of those remarkable insights. It shows that a property as familiar as mass can arise from interactions rather than from intrinsic substance. A particle that appears massive does so because the field describing it interacts continuously with a background field permeating space. The logic of the theory therefore remains intact. No rule is broken. The equations governing the fields remain symmetric at their foundation. Mass emerges naturally once the Higgs field settles into its vacuum state. The ripple associated with another field experiences that background and behaves as if it carries inertia. In this way, the theory transforms what once looked like an arbitrary parameter into a predictable consequence of field interactions. Experimental programs at the Large Hadron Collider continue examining this mechanism in detail. By measuring how the Higgs boson interacts with other particles, physicists test whether the strengths of those interactions match the predictions of the standard model. Any deviation might indicate new physics beyond the current theory. Each new dataset refines our understanding of how mass emerges through field interactions. This framework also raises further questions about the origin of the Higgs field itself. Why does the field possess the particular potential that allows it to settle into a non-zero value? Why do different particles couple to the field with such varied strengths? These questions remain active areas of research, explored through both theoretical models and high-energy experiments. The insight that mass can arise from interaction rather than intrinsic substance represents a profound shift in our understanding of matter. The particles composing the universe do not simply carry mass as a permanent label. Their mass reflects how strongly they interact with the background field that permeates space. The Higgs mechanism provides the mathematical structure explaining how that interaction operates without violating the symmetries of the theory. When the possibility of these interactions is considered, another issue becomes clear. The mechanism that allows a field to settle into a non-zero background depends on the shape of its potential. Explaining that shape leads to the question explored in why did physicists need the Mexican hat potential instead of an ordinary bowl? Why would the entire explanation of mass collapse if the energy landscape of a field looked like a simple bowl instead of the strange ring-shaped structure physicists call the Mexican hat potential? This question reveals one of the most delicate pieces of reasoning inside modern particle physics. If the potential of the Higgs field had the simplest possible shape, a smooth bowl whose lowest point sits exactly at zero, the field would settle quietly at that central point and remain there. In that situation, the Higgs field would carry no background value throughout space. The electroweak theory would remain perfectly symmetric, and the mechanism responsible for generating particle masses would fail completely. The existence of massive W and Z bosons would become impossible within the mathematical logic of the theory. This is why theorists in the 1960s realized that the potential describing the Higgs field could not resemble an ordinary bowl. Instead, it had to possess a structure whose lowest energy points lie away from the center. The energy landscape must be shaped, so that the field cannot rest at zero. Only then can the vacuum of space carry a constant, non-zero value. That requirement leads naturally to the form now widely known as the Mexican hat potential. The name comes from the visual appearance of the energy surface when represented in two dimensions. Imagine a circular hill with a raised rim surrounding a shallow central peak. The lowest points lie along a ring around that center. A ball placed on such a surface will roll away from the top and settle somewhere along the circular valley. Every location along that ring has the same energy. The system chooses one position randomly, even though the underlying energy surface remains perfectly symmetric around the center. In field theory, the Higgs field behaves in an analogous way. The potential is symmetric, but the resting state of the field lies somewhere along the ring of minimum energy rather than at the central point. The scientific significance of this structure lies in a concept called spontaneous symmetry breaking. The equations describing the Higgs field possess a symmetry that treats all directions in field space equally. Yet when the field settles into its lowest energy configuration, it selects one particular value from the entire circle of possibilities. The symmetry of the equations remains present, but the vacuum state no longer displays that symmetry. This subtle shift allows the electroweak theory to retain its mathematical consistency while still producing massive particles. To appreciate why this shape is necessary, it helps to recall how a simple quadratic potential behaves. A quadratic potential corresponds to the familiar bowl shape. If a field governed by such a potential is disturbed, the restoring influence pushes it back towards zero. The smallest oscillations around that point correspond to particles whose mass is determined by the curvature of the bowl, but crucially, the equilibrium value of the field remains zero. That means the field contributes no constant background value to space. For the Higgs mechanism to operate, the vacuum expectation value must be non-zero. That constant background interacts with other fields and modifies their oscillation patterns, producing the masses observed in experiments. If the Higgs potential had the ordinary bowl shape, the field would sit exactly at zero and the entire mechanism would disappear. W and Z bosons would remain massless waves traveling at the speed of light. Weak interactions would extend over enormous distances, altering nuclear processes and the structure of matter. Physicists recognized this difficulty while constructing the electroweak theory during the 1960s. The mathematical framework developed by Sheldon Glashow, Abdus Salam, and Steven Weinberg described electromagnetic and weak interactions within a unified gauge symmetry. However, that symmetry required the force carriers to be massless. Experiments clearly contradicted this prediction because weak interactions involve extremely massive bosons. Reconciling the theory with observation required a way to generate mass without explicitly inserting it into the equations. The solution emerged through the work of several researchers, including Peter Higgs, François Englert, Robert Brout, Gerald Guralnick, Carl Hagen, and Thomas Kibble. They explored how a scalar field with a potential shaped like a Mexican hat could allow the vacuum to acquire a non-zero value. Once the field settled into that value, interactions with it would alter the behavior of other fields. Mass would appear as a consequence of the background field, rather than as an arbitrary parameter. The concept may seem abstract, but it produces clear experimental consequences. When the Higgs field sits at a non-zero value throughout space, small disturbances around that equilibrium correspond to a particle known as the Higgs Boson. That particle was discovered in 2012 at the Large Hadron Collider. Detectors called a toroidal Large Hadron Collider Apparatus and Compact Muon Solenoid observe decay patterns consistent with a scalar particle of approximately 125 giga-electron-volts. The measured properties of this particle match the predictions derived from the Higgs potential. The existence of the Higgs boson therefore confirms that the potential governing the Higgs field must possess a structure allowing a non-zero vacuum value. If the potential were an ordinary bowl centered at zero, the Higgs boson would not appear in the way experiments observed. The discovery of this particle provides strong evidence that the energy landscape of the Higgs field resembles the ring-shaped configuration required by the theory. Observational data from cosmology also support this framework indirectly. Measurements of the cosmic microwave background radiation by the Planck mission of the European Space Agency reveal conditions in the early universe that depend on the masses of fundamental particles. Those masses arise through interactions with the Higgs field. The existence of massive W and Z bosons influences processes such as nucleosynthesis and the formation of large-scale cosmic structures. Without the non-zero vacuum expectation value generated by the Mexican hat potential, the universe would evolve in a dramatically different way. Astronomical observations performed with instruments operated by the National Aeronautics and Space Administration and the European Space Agency continue probing the consequences of these particle properties. The formation of stars, galaxies, and chemical elements depends on nuclear reactions that involve particles whose masses originate through the Higgs mechanism. Even the earliest galaxies observed by the James Webb Space Telescope rely on atomic processes shaped by the masses of electrons and quarks. Carl Sagan once observed that, "We are a way for the cosmos to know itself." The development of the Higgs potential illustrates that process in action. By examining the mathematical structure of field equations and comparing their predictions with experimental data, scientists uncovered a hidden property of the vacuum itself. The shape of the Higgs potential determines why the field does not rest at zero and why the universe contains particles with mass. One subtle consequence of the Mexican hat potential deserves attention. Although the energy landscape is symmetric around the center, the vacuum state selects one position along the ring. That choice gives rise to the phenomenon of spontaneous symmetry breaking. The underlying laws retain their symmetry, but the physical state of the universe does not display it directly. This mechanism plays a central role not only in particle physics, but also in many areas of condensed matter physics, where similar patterns appear in superconductors and magnetic materials. Researchers continue studying the detailed structure of the Higgs potential through experiments at the Large Hadron Collider. By measuring how Higgs bosons interact with themselves and with other particles, physicists attempt to determine whether the potential exactly matches the simplest theoretical form, or whether additional features appear at higher energies. Any deviation could signal new physics beyond the standard model, perhaps revealing deeper layers of symmetry or additional fields influencing the behavior of the vacuum. The Mexican hat potential, therefore, represents far more than a visual metaphor. It is the mathematical structure that allows the Higgs field to maintain a constant value across the universe. That non-zero value gives mass to several fundamental particles and shapes the interactions governing matter and energy. Without this unusual energy landscape, the electroweak theory would fail to describe the observed properties of nature. And once the role of this potential becomes clear, another question emerges naturally from the same framework. If the Higgs field fills space with a constant value, and its oscillations produce the Higgs boson, then the next step requires understanding exactly what that particle represents within the field itself. So what is the Higgs boson exactly? A new kind of matter, or just a shiver in a field already filling the universe? What if the particle announced to the world in 2012 was never truly a particle in the ordinary sense at all, but instead a measurable vibration of something that had already been quietly present everywhere in the universe since the first fraction of a second after the Big Bang? The question appears simple on the surface, yet the answer leads us into one of the most precise and experimentally confirmed ideas in modern physics. When scientists speak about the Higgs boson, they are not describing a tiny marble hidden somewhere inside matter. They are describing a specific type of motion occurring within a field that fills all of space. To understand why this matters, we need to return briefly to the structure of the standard model of particle physics. By the late 1960s, physicists had assembled a mathematical framework describing the known elementary particles and the forces that act between them. Electrons, quarks, neutrinos, photons, and several other particles could all be described within a unified system of equations. These equations worked astonishingly well. They predicted scattering experiments with extraordinary precision, sometimes matching laboratory measurements to many decimal places. Yet there was a problem that refused to disappear. The equations required many particles to behave as if they had no mass at all. In the mathematics of the standard model, the carriers of the weak nuclear force should move through space the way light moves, at the universal speed of light itself. But in reality, the carriers of that force, particles known as W bosons and Z bosons, behave very differently. They are heavy, extremely heavy for subatomic particles. Their masses are roughly 80 and 90 times larger than the mass of a proton. Something in nature was giving these particles inertia. During the 1960s, several physicists began exploring a possible explanation. Among them were Peter Higgs in Scotland, Francois Englert and Robert Brout in Belgium, and several other groups working independently. Their insight was subtle but powerful. Instead of assigning mass directly to particles, they proposed that space itself might contain a field whose presence changes how certain particles move. In physics, a field is not an abstract idea. It is something measurable. The gravitational field of Earth can be detected by dropping an object and watching it accelerate toward the ground. The electromagnetic field can be measured through the force it exerts on electric charges. In each case, the field fills space, and particles respond to it. The new proposal suggested that another field existed everywhere in the universe, a field that does not vanish, even in empty space. This field would interact with certain particles in such a way that their motion becomes harder to change. In everyday language, we call that resistance mass. The mathematics behind this proposal is precise. In the equations describing the Higgs field, the field does not settle to zero when the universe cools after the Big Bang. Instead, it stabilizes at a constant background value. Physicists call this the vacuum expectation value. Even in perfect vacuum, the Higgs field still has a non-zero magnitude. Once that background value exists, particles moving through space constantly interact with it. The strength of that interaction determines how massive each particle appears. Electrons interact with the Higgs field in a particular way, giving them their familiar mass. W bosons interact more strongly, which is why they are much heavier. Photons, by contrast, do not interact with the Higgs field at all. That is why light remains massless and always travels at the same speed. This explanation solved a major theoretical difficulty, but it also led to a remarkable prediction. If a field fills space, then small disturbances in that field must also exist. When a field vibrates slightly around its background value, those vibrations behave like particles. The electromagnetic field produces photons when it oscillates. The gravitational field produces gravitational waves when it fluctuates. The Higgs field should behave the same way. Imagine the Higgs field as having a steady background level throughout space. If that level is disturbed locally, the disturbance propagates outward like a ripple. In the mathematics of quantum field theory, that ripple corresponds to a particle, a quantized excitation of the field. That excitation is what physicists call the Higgs boson. This is the crucial point. The Higgs boson is not a separate object hidden somewhere inside matter. It is the smallest possible ripple in the Higgs field itself. The idea might sound abstract, but it has been tested with extraordinary precision. To observe such a ripple, scientists needed to concentrate enormous amounts of energy into a tiny region of space. According to the relationship between energy and mass discovered by Albert Einstein, energy can transform into particles when sufficient energy is available. The challenge was to produce enough energy in particle collisions to excite the Higgs field. This goal eventually led to the construction of the Large Hadron Collider at the European Organization for Nuclear Research near Geneva. The accelerator ring stretches roughly 27 kilometers beneath the border of France and Switzerland. Inside that ring, beams of protons are accelerated until they move extremely close to the speed of light. When the beams collide, the energy density briefly becomes high enough to create new particles that do not normally appear in everyday conditions. Among the many possible outcomes of those collisions, physicists searched for the specific decay patterns predicted for the Higgs boson. These patterns involve the Higgs particle forming for an extremely short time, then transforming into other particles such as pairs of photons or pairs of Z bosons. On the 4th day of July, in the year 2012, two independent detector teams announced that they had observed a new particle with a mass of roughly 125 billion electron volts. The statistical evidence was strong enough to confirm that the particle behaved exactly as the Higgs theory predicted. The discovery marked the final missing component of the Standard Model. Yet what truly captures the imagination is not merely the particle itself, but the concept it represents. The Higgs boson demonstrates that the properties of matter can arise from interactions with fields that permeate the entire universe. Mass, which once seemed like a basic intrinsic feature of particles, emerges from a deeper structure in the vacuum of space. Physicist Richard Feynman once remarked that the imagination of nature is far, far greater than the imagination of man. The Higgs boson illustrates this point beautifully. Instead of discovering a hidden grain of matter that gives weight to the universe, physicists uncovered evidence that empty space itself contains a dynamic field whose subtle presence shapes the behavior of fundamental particles. The field does not sit quietly in laboratories. It extends across galaxies, across interstellar space, and through every atom of every object around us. Whenever particles move through the universe, they are interacting with that field. The ripple we call the Higgs boson simply reveals that the field is there. Modern experiments continue to explore this discovery in greater detail. Measurements of the Higgs boson's mass and decay patterns help physicists test whether the Standard Model is complete or whether additional particles might exist beyond it. Some theories predict heavier cousins of the Higgs boson or additional fields that could help explain dark matter or the early expansion of the universe. Future accelerators may investigate these possibilities with greater sensitivity. Projects under discussion in Europe and Asia aim to build even larger particle colliders, capable of studying the Higgs field with extraordinary precision. By measuring how strongly the Higgs boson interacts with other particles, scientists hope to determine whether the field behaves exactly as the Standard Model predicts, or whether subtle deviations point toward deeper layers of physics. Astronomical observations also provide clues. The same quantum fields that govern particle physics played a role during the earliest moments of cosmic history. Satellite missions studying the cosmic microwave background radiation, such as those conducted by the National Aeronautics and Space Administration and the European Space Agency, measured tiny fluctuations in the temperature of the early universe. Those fluctuations originated from quantum processes in primordial fields that existed when the universe was less than a second old. The Higgs field itself may have influenced how the universe cooled and evolved during those early moments. Some cosmological models even suggest that interactions involving the Higgs field could help explain why matter survived after the Big Bang, instead of annihilating completely with antimatter. These investigations are still unfolding, but the central idea has already transformed our understanding of matter. The Higgs boson revealed that particles are not isolated objects moving through an empty stage. Instead, they are excitations of fields that fill the cosmos. And as physicists continue to examine the properties of this remarkable field, another puzzle begins to sharpen into view, one that carries the exploration forward into the next chapter of this journey through the foundations of reality. If the Higgs boson is only the smallest ripple in a field that permeates all space, then a deeper challenge waits quietly ahead. Could the same field that gives particles their mass also determine whether the universe itself is stable, or whether the vacuum surrounding us is only temporarily balanced in a state that might one day change? If physicists knew the mechanism, why couldn't they predict the Higgs mass before the collider data arrived? Why did the Standard Model describe the Higgs mechanism with extraordinary precision for nearly half a century, yet remain unable to tell physicists one of the most basic numbers they wanted to know: the mass of the Higgs boson itself? This puzzle became one of the most persistent tension points in particle physics. The mechanism explaining how particles acquire mass was already understood in principle by the late 1960s. The vacuum expectation value of the Higgs field was constrained by measurements of the weak force. Yet the mass of the Higgs boson remained hidden until experimental data finally revealed it at the Large Hadron Collider in 2012. The reason lies in a subtle detail inside the Higgs potential. Physicists could determine where the field rests in the vacuum, but they could not determine how steep the energy landscape is around that resting point. To understand the problem clearly, it helps to recall what the Higgs boson represents. The Higgs field fills all space with a constant background value of approximately 246 giga-electronvolts when expressed in energy units. This value was not guessed arbitrarily. It was inferred from precise measurements of the masses of the W and Z bosons, the carriers of the weak nuclear interaction. The electroweak theory relates the masses of those particles directly to the strength of the Higgs field in the vacuum. Once the masses of the W and Z bosons were measured in particle accelerators during the 1980s and 1990s, the value of the Higgs field could be deduced with remarkable accuracy. But knowing the resting value of the field does not automatically reveal the mass of its quantum excitation. The Higgs boson corresponds to a ripple around that resting value. The energy required to create that ripple depends on the curvature of the potential near the minimum. If the potential is steep, the oscillation frequency is high and the particle is heavy. If the potential is shallow, the oscillation frequency is lower and the particle is lighter. In mathematical language, this steepness is controlled by a parameter, often called lambda. In physical terms, it represents how rapidly the energy of the field rises as the field moves away from its equilibrium value. The difficulty is that the Standard Model does not determine this parameter by itself. The theory requires the existence of the Higgs field and specifies how it interacts with other particles, but the steepness of its potential remains a free quantity. In practical terms, this means that the Higgs boson could, in principle, have had a wide range of masses consistent with the rest of the theory. Some theoretical analyses suggested values as low as 100 giga-electron volts, while others allowed masses several times larger. Without experimental data, the exact value remained unknown. This situation illustrates an important aspect of scientific reasoning. A theory may describe a mechanism clearly while still containing parameters that must be measured experimentally. The Standard Model explains how particles obtain mass through interaction with the Higgs field, yet the exact numerical properties of that field require observation to determine. The mass of the Higgs boson, therefore, became one of the most anticipated measurements in modern physics. During the 1990s and early 2000s, experiments at the Large Hadron Collider at the European Organization for Nuclear Research searched for the Higgs boson. These experiments gradually eliminated large regions of possible masses. When the collider shut down in 2000, the remaining allowed window pointed toward a relatively light Higgs boson, though the exact value was still uncertain. The search then shifted to the Large Hadron Collider, designed specifically to reach the energies necessary to produce the particle if it existed within the predicted range. The moment of discovery arrived on the 4th of July in 2012. Two enormous detectors, known as a toroidal Large Hadron Collider apparatus and compact muon solenoid, independently reported evidence for a new boson with a mass near 125 giga-electron volts. The signal appeared in several decay channels, including pairs of photons and pairs of Z bosons. Statistical analysis showed that the probability of the signal arising from random background fluctuations was extremely small. The result quickly reached the level known in particle physics as 5 sigma significance, the threshold typically required to claim a discovery. The measured mass of the Higgs boson corresponds to roughly 130 times the mass of a proton. This value sits in an intriguing region of theoretical predictions. It is heavy enough to allow the Higgs field to stabilize the electroweak symmetry breaking mechanism, yet light enough that quantum corrections do not immediately destabilize the vacuum. Physicists soon realized that this mass places the universe near a boundary between absolute stability and a state known as metastability. In such a scenario, the vacuum of the Higgs field remains stable for times far longer than the current age of the universe, but may not represent the deepest possible minimum of the potential. Following the discovery, experimental teams devoted years to refining the measurement. The Large Hadron Collider produced millions of Higgs bosons through high-energy proton collisions. By analyzing their decay patterns with increasing precision, researchers were able to determine the mass of the particle with remarkable accuracy. Measurements from the toroidal Large Hadron Collider apparatus collaboration have now reached a precision approaching 0.09%. What began as a theoretical placeholder has become one of the most precisely measured quantities in particle physics. The importance of this measurement extends beyond the Higgs boson itself. The exact mass of the Higgs influences how the Standard Model behaves at extremely high energies. Calculations combining the Higgs mass with the mass of the top quark allow physicists to examine the long-term stability of the Higgs potential. If the Higgs mass were slightly larger, the vacuum would appear completely stable across all energy scales. If it were slightly smaller, the theory would suggest a universe where the vacuum could eventually transition to a lower energy state. The measured value lies intriguingly close to the boundary between these possibilities. Observations from cosmology also depend indirectly on these parameters. Measurements of the cosmic microwave background radiation by the Planck satellite of the European Space Agency reveal the distribution of matter and energy in the early universe with extraordinary precision. The behavior of fundamental particles during the first moments after the Big Bang depends on their masses and interaction strengths. The values measured for the Higgs boson and related particles fit consistently with the framework used to describe cosmic evolution. Astronomical instruments operated by the National Aeronautics and Space Administration and the European Space Agency continue probing these early conditions. Observations from the James Webb Space Telescope explore galaxies formed within the first few 100 million years after the Big Bang. The processes shaping those galaxies rely on atomic and nuclear interactions, ultimately determined by the masses of fundamental particles. In this way, the value measured in collider experiments connects directly to the structure of the observable universe. Carl Sagan once observed that science is a way of thinking much more than it is a body of knowledge. The story of the Higgs mass illustrates that principle clearly. Physicists understood the mechanism generating mass long before they could measure the particle responsible for it. They constructed experiments capable of testing the theory, gradually narrowing the range of possibilities until the correct value emerged from the data. The final number was not chosen by theoretical preference. It was revealed through observation. Today, the Higgs boson occupies a central role in the Standard Model. Its mass is now measured with high precision, yet its deeper implications continue to challenge researchers. The shape of the Higgs potential, the stability of the vacuum, and the possibility of additional fields interacting with the Higgs remain open questions. Experiments at the Large Hadron Collider continue exploring these possibilities by studying how the Higgs boson interacts with other particles. Once the value of the Higgs mass was measured with high precision, attention shifted to a broader issue. What role does this particle actually play in the universe? Did the Higgs boson explain all mass, or only reveal one layer of a much larger problem? Did the discovery of the Higgs boson finally explain why everything in the universe has mass, or did it only illuminate one layer of a much deeper structure still hidden beneath the surface of modern physics? This question sits quietly behind the excitement of the 2012 discovery. When the Higgs boson was confirmed at the Large Hadron Collider, headlines around the world often called it the particle that gives mass to everything. The phrase was simple and memorable, but it was not completely accurate. The Higgs mechanism explains an essential part of the story, yet it does not account for most of the mass that makes up the ordinary matter surrounding us. To see why, it helps to examine carefully which particles obtain their mass through the Higgs field and which do not. Within the framework of the Standard Model, the Higgs field interacts with several fundamental particles. The carriers of the weak force, known as the W and Z bosons, obtain their masses through interaction with the Higgs background field. Without this interaction, they would behave as massless waves, similar to photons. Their large masses, roughly 80 and 90 giga-electron-volts respectively, arise because the Higgs field modifies the oscillation patterns of the fields describing these particles. The same mechanism also provides mass to elementary fermions, such as electrons, muons, tau leptons, and the 6 types of quarks. Each particle interacts with the Higgs field with a specific strength, and that interaction determines the magnitude of its mass. The photon behaves differently. Photons do not interact with the Higgs field in a way that produces mass. As a result, the electromagnetic force remains mediated by a massless particle. This property allows light to travel across the universe at a constant speed of approximately 300,000 kilometers per second in vacuum. Observations from telescopes operated by the National Aeronautics and Space Administration and the European Space Agency confirm that photons propagate across billions of light-years without showing evidence of rest mass. Gamma rays emitted by distant supernova explosions and active galaxies arrive at Earth in patterns consistent with a massless electromagnetic field. The Higgs field therefore explains why certain fundamental particles possess mass, while others remain massless. Yet an even more striking fact appears when one examines the structure of ordinary matter. Most of the mass in the visible universe does not come directly from the Higgs interaction at all. Protons and neutrons, which form the nuclei of atoms, contain nearly all the mass in everyday objects. The proton has a mass of approximately 938 mega-electron volts, far greater than the masses of the quarks inside it. When physicists add together the intrinsic masses of the proton's constituent quarks, they obtain only a small fraction of the total. Where does the rest come from? The answer lies in the dynamics of quantum chromodynamics, the theory describing the strong nuclear force. Inside a proton, quarks are bound together by gluons, particles that carry the strong interaction. These gluons constantly exchange energy with the quarks, producing a highly dynamic system in which energy is stored in the fields themselves. According to Albert Einstein's relation between mass and energy, energy confined within a system contributes to the system's mass. The majority of the proton's mass therefore arises from the intense motion and interaction of quarks and gluons, rather than from the Higgs field. This insight emerged gradually through theoretical work and through experiments studying the internal structure of protons. During the 1970s and 1980s, deep inelastic scattering experiments at facilities such as the Stanford Linear Accelerator Center revealed that protons contain smaller constituents, moving with high momentum. Later experiments at the European Organization for Nuclear Research and other laboratories confirmed that gluons carry a substantial portion of the proton's internal energy. Modern calculations using lattice quantum chromodynamics reproduce the observed masses of protons and neutrons by simulating the interactions of quarks and gluons on powerful supercomputers. In practical terms, this means that the Higgs field sets the masses of fundamental building blocks, but the mass of composite particles emerges largely from the energy of their internal dynamics. The proton illustrates this clearly. Its quarks interact through gluon fields that confine them inside a tiny region about 1 femtometer across. The constant exchange of energy between these fields produces most of the mass we measure when weighing ordinary matter. Astrophysical observations reinforce this understanding. The processes powering stars depend on nuclear reactions involving protons and neutrons. Observatories operated by the National Aeronautics and Space Administration and the European Space Agency study stellar interiors where hydrogen nuclei fuse into helium. The mass difference between these nuclei releases energy according to Einstein's principle that mass and energy are equivalent. The fact that most of the proton's mass arises from strong interaction energy plays a crucial role in determining how stars generate light and heat. The connection extends further into cosmology. Measurements of the cosmic microwave background radiation by the Planck satellite reveal the distribution of baryonic matter in the early universe with extraordinary precision. The gravitational influence of protons and neutrons shaped the growth of cosmic structures such as galaxies and galaxy clusters. Because the majority of their mass arises from quantum chromodynamics rather than directly from the Higgs mechanism, the behavior of strong interactions indirectly influences the large-scale structure of the universe observed today. Astronomers using the James Webb Space Telescope continue examining galaxies that formed within the first few 100 million years after the Big Bang. The formation of these early galaxies depends on the cooling of gas clouds, composed mainly of hydrogen and helium. The atomic properties governing that cooling process depend on the masses of electrons and protons. Electrons obtain their mass through interaction with the Higgs field, while the proton's mass arises mostly from the energy of quark and gluon interactions. Together, these mechanisms shape the conditions, allowing stars and galaxies to emerge. Carl Sagan once wrote that somewhere, something incredible is waiting to be known. The Higgs boson discovery illustrates this idea in a particularly clear way. When the particle was observed at the Large Hadron Collider in 2012, it confirmed a crucial element of the Standard Model. The mechanism responsible for giving mass to several fundamental particles had finally been verified experimentally. Yet the discovery also revealed how incomplete the explanation still is. The Higgs field accounts for part of the mass story, but the dynamics of quantum chromodynamics explain most of the mass contained in ordinary matter. This realization does not diminish the importance of the Higgs discovery. Instead, it expands the scope of the scientific journey. The Higgs mechanism solved a puzzle that had challenged physicists for decades. At the same time, it highlighted the deeper complexity of matter. The universe generates mass through multiple processes, each governed by the interactions of fundamental fields. Modern research continues probing these interactions with increasing precision. Experiments at the Large Hadron Collider measure how the Higgs boson interacts with other particles. Lattice quantum chromodynamics calculations refine our understanding of how quark and gluon energy contributes to proton mass. Astrophysical observations extend these insights across cosmic scales, linking the smallest known particles to the largest structures in the observable universe. The story, therefore, does not conclude with the discovery of a single particle. Instead, it reveals a layered structure of physical laws in which several mechanisms combine to produce the matter we observe. The Higgs field provides mass to fundamental particles. The strong interaction transforms energy into the bulk of the mass inside atomic nuclei. Together, they shape the physical world. And as this long exploration reaches its final moment, the deeper message becomes clear. The Higgs boson did not end the search for understanding. It opened a wider landscape of questions about how the universe builds matter from fields and energy. Thank you for spending this quiet stretch of time exploring one of the most subtle discoveries in modern physics. Your curiosity and patience make journeys like this possible. As the night continues and the universe outside keeps moving through its silent patterns of fields and particles, may your thoughts settle comfortably and your rest come easily. Good night.